Welcome to Radar System course. Today we start conical scanning and its sequential loading here. So we have seen that a monopoles tracker, so in which we supposed to send a monopulse, single pulse to the various beam antenna, and then we need to track whatever the echo signal received. Based on that echo signal received, so we need to identify or we need to track the target there. And in this case, we just send a signal through the various beams of antenna. So means we have a single pulse. Okay, that single pulse is to be sent to the multiple antennas. We have seen earlier that is about sending the pulse through the two antennas, and then we have seen that same signal is to be sent through the four antennas, then five antennas, and through that we are able to measure what will be the range of the target, and then we need to measure the what will be the angle of the target, position of this target means location. So that position or location in terms of what? A azimuth, or you can say that in terms of a elevation. So what will be the range position of the target in terms of a azimuth and a elevation that we need to be obtained here. So now for identifying or for understanding what will be the position of the target, so we need to know about that what will be the type of scanning we supposed to use, or we need to know about that what beam or what signal we send to the a target there. So in earlier case we say that we can use a monopulse, okay, that is to be used through the single antenna, multiple antennas, then you can measure that azimuth, elevation as well as the range there. But instead of that, if we consider that we send a pulse, okay, and that pulse is to be sent with a different timing. So at one particular instant we send a pulse, we receive the echo. Then in the second instant we send a pulse, we receive the echo. Okay, so now we can say that we are just send a signal to the target, or we are sending the pulse to the target with a time sharing basis, and that signal we transmitted through the time sharing basis, or you can say that a beam form based on the time sharing basis, and that will be used to measure the a range as well as the angle, that is about the azimuth and elevation. And that sharing the time using a single antenna beam, okay, sharing that particular means we say that at instant one instant we send a signal, another instant we send a signal, everything is based on a single antenna, means we are just sharing the single antenna based on the time there. And in this case what happened, we require only a single antenna instead of a multiple antennas we are used in a monopoles tracker. So we use only a single antenna based on the time sharing, and that will be used to measure the range as well as the azimuth and elevation there. And that time sharing, or we can say that we are just switching the beam through this two different point or two different positions through the time sharing, that is called as a sequential loading. Okay, so we can say that sequential loading is used to measure the what will be the angle in terms of azimuth and elevation of a target, as well as that will be useful for the measurement of the range here. And that particular switching of, or we can say that time sharing of a single beam antenna, that particular switching is called as a sequential lobing, or we can say that a sequential switching, or we can say that a lobe switching. Now we can consider that a lobe switching means what? Lobe means what? We generally say that antenna radiation pattern. This one, radiation pattern formed by an antenna, and this in this case we consider that here a maximum amplitude. Okay, you can say that this one is about the maximum amplitude. So in that case we consider this one is about a position 1 from the a single lobe. Okay, this one is about the position 1 from the a single lobe. And then if I consider that in another case here, so I supposed to use this one, okay, this one now. Now in this case, this one is about what we can say that this one is about a position. Means this two beams. Okay, so we are getting the two lobes from the single antenna or a single device. If we use only a single device, and then through the single device we are getting these two lobes. And if you consider where will be our target, so target will be a position, in this case in between this position P1 and P2. Suppose I say that a target position is here. Okay, this is about our target now. Okay, so now I consider that this one is about a target position. Now this target position we can consider here right now. This one is about a target position T. Now at this case supposed to be this one is about a target position. So we are getting one position, means here we are getting the maximum value, or we can say that maximum amplitude. Here we are getting the maximum amplitude, means position 1 and position 2 from the single beam with the time sharing concept. And then we are getting the, we say that our target may be here, means bore site of a target, bore site is here. So in that case we can say that this one is about a target. So bore site of antenna position is P1, bore site of this particular lobe will be put P2, but our target position is here. So that's why the bore site, whole bore site will be towards this particular target here. Now we are getting these two different lobes here through the switching pattern. Okay, time sharing switch. Okay, so we can say that in a single pulse we say send a pulse to this one. This is about a lobe formation by this thing. Okay, lobe formation within a given particular period of a time. This one is about a lobe formation for this another time. Okay, so in that case we are just switching the position, changing the angle position. So this is about the difference between this P1 and P2. It is called the angular deviation between these two particular lobes. But target present is here. Okay, here is our target. So in that case, if the target is here, so what will be the squint angle between this beam, this one, P1 and P2. But if you consider that a target is here, so from this particular position, we need to find out that what will be the squint angle. So this one is a polar representation. If I suppose to consider a rectangular representation there, so in that case, we consider that this one is about a position of a target. This one we can say that a P1 now. Okay. So now I consider the target position here, and I suppose to consider that, okay, so I suppose to consider that this one now here. Okay, so in that case a target position is here, that is about a P2. Okay, position of this particular row. But if you consider instead of that, the main axis, this one is about main axis, your axis is going to be switched here. Okay, so what about the position there? So target position may be here. Okay, target position may be here. Okay, in between this P1 and P2. So from this we can say that a position of a target, suppose I am supposed to I consider that this one is about a T is the target position, and a beam switching position. This one is about a beam switching position. Here we can say that at this particular point the amplitude is a different here. Okay, this is about the a beam switching. That is about a switching axis. So now we can find out it, what will be the location of a target when we consider that either a polar representation, or we can say that a rectangular representation. So we obtain the difference in the angle there. Okay, and through this we can find out what will be the azimuth and elevation. Okay. Position of the beam we are just changing here, and in which direction we are changing, bore site of an antenna. So means here we can say that your target is present in this bore side of an antenna. Now in this case, this one is about a switching axis. We are supposed to consider that this one is nothing but the bore side, but the target is not present at a bore side axis or bore side position. Okay, this one is switching axis. The target is here now. So through that we can find out the difference in the amplitude between the that two switching position here. Okay, here. Okay, so likewise, if I consider that the switching position as per the target is here, and this one is about a switching axis. In that case, there will be the difference in the amplitude, but here in the case, there will be the difference in the amplitude where the target location is present. So now, which particular lobe that will provide you the exactly displacement in terms of what we can say that the angle here through the switching position. So this one, if I consider that P2 here right now, so toward this particular P2 position of the beam, so in between that from the switching axis to this target. So if you find out what will be the angle there, and that angle is called as a switching angle, or you can say that that is about the angular displacement of a target from this switching axis there. Means we can find out that the target is present here, okay, that toward the bore side, but it is moved in or it will be displaced in the AP2 lobe here. Okay, so means this one is about a position, or you can find out the position. So these are the lobes, or you can say that these are the lobes generated through the echo signal received, and from that we can find out the what will be the positions of this particular beam here. Okay, and position P1 and P2 means what? We are getting the echo signal from this. Okay, it has maximum here. We are getting the echo signal received from the target is my maximum. Okay, that is about the position, but at actual the target is supposed to be here. Okay, so then we need to find out the target is supposed to be on the axis. Here, which axis? Either at the P1 or P2, or we can say that either in the switching axis. Okay, or we can say that the target is to be present at the switching axis direction there. So this way we can find out that angle measurement in between the a target here. So right now, if I consider that, so where this target is moving, the target is moving through towards this direction because it is present in this P2 now. Okay, position is changed. And from this to this, we can find out what will be the measurement in terms of angle. Okay, angle is varying, but it is about in which direction, this direction. So this one, if you consider in terms of amplitude or not, so what will be amplitude at this position? I suppose to draw the amplitude here P1. Okay, I draw that is about the amplitude of the P2 here. That is about the position here, and then through that we can say that we supposed to move the switching axis toward this given direction. Okay, so then we can find out the target will be at this given particular position. So this one is about the motion of the a target here, movement of the target. So in this case, what happened in a sequential loading? Okay, this one is about a we just learn about the time sharing basis, and that case is called as a sequential loading. And in this particular case, we supposed to send a single pulse, okay, and then we need to receive at the given particular period of a time, and then that that pulse we are getting. So there is a small difference in the angle. Okay, that is called as a squint angle here. Means we can say that a echo signal pulse we are receiving that will be squinted toward the right position. Okay, motion here. Okay, that needs to be right. Again, if you consider that, again we change the position of the target, then we need to find out that. So again, we send the pulse. We need to find out what will be the position of the target there, and we need to change the position through sending the pulse and automatically lock that particular axis or particular position of the target there. either that beam position, if you consider that from this P2 and P1, if I consider, so from position P1 the target is right side here, from the position P2 the target is towards the left side. Okay, so from the given particular position, means we can say that here the beam is squinted towards right or beam is squinted towards left here. Okay, so that is about the splint angle, means what, position of the target there. So our aim is about to find out what will be the switching position of the target, whether it is toward the right or toward the left here, and that position is useful to track the radar there. So this case here we learn in terms of a polar coordinate system, or we can consider in terms of rectangular coordinate system, and we can find out whether that beam is to be switched, that will be the in the given particular position. Okay, and here we just send a pulse toward the target. If this antenna is rotating in both the directions, then we need to find out the position, whether it will be up or whether it will be a down. So here we just consider that right and left. If it is rotating one, so we can find out the position, so it is for the up or down. So we have seen earlier that is about a monopoles tracking system. In a monopoles tracking system, four antennas we have, and that four antennas, where then send a pulse, then these four antennas receive the echo signal, and from this measurement of amplitude of the echo signal, we can find out the what will be the error in terms of azimuth and elevation, so angle error. Okay, so whether it will be up or down, or we can find out what will be the range. So similarly, using a sequential lobing or a conical scan method, we can find out the range as well as the azimuth and the elevation there. So now we will go here, instead of a sequential lobing. Okay, instead of sending based on the time sharing, we send the pulse. Okay, instead of that we use a pulse, or we send a signal, and that send a signal through the concept of what, a conical scanning. Okay, so means what here, the concept of a conical scanning. So your signal is sent by the radar here. Okay, this one is about a radar here. So here we are getting the low. Okay, this one is about a irradiation pattern of a antenna here. Okay, this is about a lobe is generated, or we can see that this one is the position of this particular antenna now. Now, what will be the a target axis here? Okay, what will be the beam axis? So if from this lobe, if I consider that this one is about our a beam axis. Okay, so we can say that this one is about a beam axis. Okay, this one is about a beam axis. And then in a conical scanning, what happened? We need to rotate the antenna. Okay, we need to rotate the antenna. So what will be the axis of rotation, and what will be the angle between the axis of rotation and the antenna beam here? So this one is about the beam axis, and I suppose to say that that antenna is rotating. So some from example I say that this one, we have the antenna position right. We can say that it is rotating likewise. Okay, so to the given particular target. So means we are getting a signal, or we are getting the echo signal through this a rotation of the antenna there. So now how, what will be the rotation axis of the given particular beam? Okay, so we need to find out the rotation axis and what will be the position of the target here, and then that position of the target and the beam axis that will provide you the angle. Okay, so now we can consider that a position right now. Okay, so if I consider that a rotation axis, and I supposed to consider there will be the target. Now this one is about the position of the target. This one is about a target now. Okay, this one is about a target, and then this one is about a rotation now. Okay, this one is about a rotation axis. Now this beam is rotating. Okay, this beam is rotating likewise. So we can say that this beam is rotating, and this one is about a rotation axis. Now I consider that target position is here, and from this particular beam axis, this one is about the, here we are getting the maximum amplitude. Okay, so from this particular beam axis. Now from this maximum beam axis, okay, the maximum angle, and here it is rotating. So what will be the squint angle here? The squint angle is nothing but what? The angle between the axis of rotation. This one is about the axis of rotation and the axis of the antenna beam. So wherever we are getting the beam axis, that angle is called as a squint angle. Okay, so in this case, I consider that the angle here, that is about a squint angle. That is from the red to this one green. Okay, this one is called as a squint angle. The axis of rotation is from beam axis and from the rotation axis. Okay, this one is about a rotation axis. This one is about a beam axis, and this one is about a target axis. Okay, here is the target position. So now from this we can find out the what will be the beam. Generally, what happen here? The squinted angle, that is about a squint angle, it changes based on the whatever the rotation. So because that beam, it is rotating, so from the beam axis to this particular thing, it will be changes here, and echo signal we are receiving. Okay, so from that we can find out from this what will be the rotation frequency of this particular beam, and that rotation frequency of the particular beam is called as a that that called as a scanning, and that scanning in terms of a conical form, so it's called as a conical scan. Okay, so because echo signal will be modulated at a frequency that will be equal to the what will be the rotation of the beam axis here. And here we are getting the amplitude at this particular phase, so that's why we can say that the amplitude modulation, again it will be depending on the what will be the angular distance between the target direction and the rotation axis here. And then we can find out the location of the target in a two angle coordinate system. So we will get that from this what will be the change in the angle here. Okay, and that particular beam axis as well as this rotation target, that will provide you the what will be the phase of the conical scan modulation, and then that conical scan modulation to the in terms of what will be the a beam rotation, because we are getting the squinted angle there. That's why we supposed to find out the what will be the a phase here. Okay, and then we can find out, so from this particular echo signal, we are just getting that what will be the position of the a target. So we can find out, so phase means in terms of what we can say that a, how we are rotating, in which axis we are rotating. If we are using rotation only in a given particular direction, so we are getting the phase. If we are rotating in the two different manner, okay, so toward this direction or toward this direction, like, so according to that we are getting that difference in the angle in terms of a azimuth and a elevation. So instead of using the fixed position of a rotation axis in the terms of a conical scanning, we say that only in a given particular direction it is rotating now. So instead of that particular rotation axis, if the direction of the target is changes, so this doesn't work. So we need to rotate this beam toward this direction as well as in this direction. So that's why we need to know about the what will be the position of the target. So line of sight of the target, and that line of sight of the target, that will provide you the rotation, or that will provide you the angle in which direction that antenna is to be rotated here. So that's why we need to use a different servo motor. One servo motor is useful for the azimuth, one servo motor is useful for the elevation. So what will be the elevation angle and what will be the azimuth? So that will be obtained through these two different motors. So we can rotate the antenna in a given particular direction, or we can say that rotate the antenna in the given direction. So we can find out the azimuth as well as the elevation. So we need to find out where is the position of the target. Okay. So when the antenna is directed toward the target, so in that case, the conical scan modulation will be a zero amplitude here. Okay, from this particular case. So and then through that we can find out the what will be the azimuth and the elevation. So now how to go through angle tracking using the conical scan tracking. Okay, so we will consider right now a conical scanning now to the angle tracking here. So block diagram of a conical scanning track radar here. In this case, we use a antenna. That antenna is about a parabolic dish antenna. So in a parabolic dish antenna, so here we have the supposed to be axis now. So where we are going to put the antenna here. Okay, if that antenna, this one is about a primary antenna, and this one is about a secondary antenna. Means this one is a reflector. So position of a primary antenna, if supposed to be on axis is there, we are getting the lobe in the given direction. Okay, we are getting the radiation pattern in the given direction. If the position of this antenna is not on the axis, if it is the off axis, okay, supposed to be I am saying here, if it is supposed to be off axis, even we are getting the same point. But this will not act as an obstacle there, but we are getting the position in a proper direction. Now our aim is here to rotate the antenna. So that's why what thing is to be rotated? This parabolic dish is to be rotated. So in this case, we rotate a parabolic dish antenna. So it will rotate in the given direction. Okay, in this given direction. Okay, so this one we can rotate here likewise, or we can rotate in the a given direction. So this way we will find out the what will be the azimuth as well as the elevation. Now we proceed here. So consider the dish antenna first, and then in a dish antenna, so we consider that off axis antenna. Okay, so for our example, to understand that whatever the position of the antenna, likewise. Okay, so this one I suppose to consider this one is about the antenna now. So for this particular antenna, we need to rotate. So here we need to rotate here this particular antenna. Okay, so in that case, this one is about antenna. We need to rotate the antenna. Okay, so I suppose to consider that this one is about the rotation. These are the a rotor here, and that rotors to be used. These are the motors that will be used to rotate the antenna in the given particular direction. Okay, so likewise, so we consider a different types of a rotation in the different way here. So how many servo motors we require for rotating the antenna here? We supposed to consider that likewise a rotation. Okay, and then we need to provide a, a transmitter here. That one is about a transmitter. For the transmitter, we consider both. That's why we consider that one is about a duplexer here, and then that will be given to the antenna. Okay, this one is given to the antenna. So both the case. Okay, so means we are receiving the same signal. So that's why a receiver here with automatic gain control. Here, say that AGC now. Then this one receiver is a super heterodyne, so we require a second detector. It is about a second detector. Then a range gating, it will just what that range gating is useful for changing the pulse, okay, extending the pulses there. That's about a range gating here. So we use the motors, different motors we use. So this one is about a motor, and from this motor we are getting the elevation angle. So this one is about a elevation curve amplifier, and here we use for the, we are giving the feedback to this, okay. Elevation angle detector, okay. Error detector, elevation angle error detector now. And then we consider that the azimuth motor, this one is azimuth servo amplifier, azimuth servo amplifier, and this one is about the azimuth angle error detector. So means we can use this position to find out the azimuth and error. So what about the position once we got? So we can log the given particular target in the given position. So this one is to be useful. So for this we need to give the, what will be the error signal from the range gate. This one, okay, we can say that the error signal we are getting, that is from the range gate. Okay, so this one we are getting the from the range gate. Second detector, okay. So this one, and this, whatever the angle variation is used, so that that particular motor is to be rotated in a given particular direction. And for each and every motor, some signal is to be given or some signal be received. So these are the motors useful for the scanning. Okay, this one is about the scan motor. This one is about a azimuth motor. This one azimuth, and this one is about what? We can say that elevation servo motor. This one is about a elevation servo motor. Okay. So now this azimuth and elevation, these are the signals, whatever the reference signal generated through the motor, that is about it through the scanning. And that reference signal scanning, that will be the input given to the elevation angle tracker, as well as the signal is given to the azimuth angle tracker. So this one we can consider. So we are getting this two particular signals. One is to be given to this, okay, so this one we supposed to given to the angle tracking here, okay, for the elevation tracking, and one is for the azimuth angle tracking. So this one, if we consider that this particular antenna, so here we are getting the radiation pattern. Okay, so if I draw the radiation pattern, so radiation pattern will be like this, and this one is about a rotating in the a given particular direction. So we can consider a rotation in the given particular a direction. We are not able to see. I can redraw here. About a radiation. Okay, so that is about a rotation axis. So through this, we are getting a conical. This one is called as rotation toward the axis, that is called as is conical scanning now. And then toward the azimuth and the elevation. Okay, so that is about a rotation axis here. So now in this case, how we are supposed to feeding the antenna? Okay, based on that, this particular antenna will provide a given particular polarization. For example, we say that we require horizontal polarization, vertical polarization. Okay, so everything is depending upon the what feed we are using. If this antenna is rotating, so there may be the changes in the polarization. Okay, so because we need to maintain the polarization, so that's why we need to use the rotation in such a way that that antenna polarization is to be maintained here, and that particular maintaining the polarization while rotating the given particular field, that's why it is called as a nutating field. Okay, and that nutating field, because that will use at a rotating field, and then it will not changes in the polarization, as well as it will not any changes in the variation in the amplitude. Okay, so this way just we can consider that a variation in the amplitude or variation in the polarization, it will not occur, and because of that target can be identified easily. So means target accuracy in the case of a angle as well as a range, okay, that will be improved. So this particular condition, because antenna is rotating in both the direction, this particular condition is useful for the missile. So in that case, the target can be locked or a target position is to be obtained. So what will be the rotation speed of this particular antenna? In that case, it will take a 30 revolution per second. Okay, so that is about a speed of this rotation of this antenna. This motor, whatever the scanning motors we are using, they are rotating at a 30 revolution per second here. And this technique is useful for in, in a war or guiding the missiles and all, so that we can lock the given particular target or identifying the target or provide the position to the a missile there. Okay, or given the direction to the missile or provide them direction to the missile. So these are the motors that will rotate. Then azimuth and elevation, these are the two different motors that are useful to find out what is the phase there. So that's why here the reference phase generator is used, and this one is nothing but a reference phase generator, and that reference phase generator that will provide a signal to the azimuth as well as for the elevation there. So generally, if you consider that azimuth and elevation, means we can consider this one is about what you can say the elevation now. And if okay, so in which direction? So we can suppose to consider that the position. Okay, so right now I say that this is about the earth now. Okay, so in that case, this one is about the target. So whatever the angle we are getting, that is called as the elevation. Okay, so this one is called. And azimuth means what? From this to this. Okay, so this one is about the azimuth here, position. So in that case, we supposed to consider a target. Okay, we supposed to consider that a spherical coordinate system, and we can find out what will be the azimuth here. Okay, so that is about we can use these two different motors for azimuth. And we say that a transmitter and receiver. So this one is about a it receiver is about a superuterine structure. Okay, so that's why we use a second detector here, and that second detector is used to extract the whatever the error signals present in the given particular echo signal or a receiver. And then we can consider this a range gating here, or a what you can say that uh, range gator, and that is useful for identifying whatever the pulses we have, and that particular pulses, whatever the pulses we are train of pulses we are receiving, and that particular train of pulses is to modify or is to be extend the pulses there, or in another way, in a simple manner, we say that that range gating is nothing but used as a low pass filter, and as well as that will be used as a sample and hold circuit. Okay, so it's just like stretching the given particular pulse within a particular direction. So that's why we can say that in another word, range gating is called as a boxcar generator here. Then we consider a elevation angle error detector, azimuth angle error detector. We need to find out what will be the position of the angle, whether it is up or down, whether it is right, whether it is left, or whether it is right up, left up. Okay, likewise. So that's why we consider that whatever the error signal generated through the particular comparison of a whatever the pulse repetition frequency signal or whatever the echo signal we have received. So through that we can measure the difference in the angle here. Okay, so now these are about a conical scanning tracking radar, and again one more function. If you see that here, these are the amplifier. Okay, so whatever the errors are there, that is to be provided to the given through the motor, so that whatever that rotation can be controlled toward the given particular direction. So in which particular direction, what will be the position, everything that is about controlled by the scan motor, azimuth motor, as well as the elevation motor. So everything is to be controlled there through the a signal we have received through the conical scanning here. Now in this case, a transmitter, we can consider a duplexer here. Duplexer, we know that as a switch at a transmitter, it allowed to transmit the signal towards the antenna. At time of a receiver, it provide the signal to the receiver here. Then we have the automatic gain control here. So that is useful for whatever the errors are there, or we can say that if is there any variation in the amplitude or is there is variation in the level of the signal. So AGC will control that particular level of the signal, or they are just maintaining the signal level, or we can say that whatever the amplitude variation is there, so that can be maintained through this automatic gain control. And these particular motors, whatever the signal we are receiving from this range gate, this particular motor is to maintain the whatever the splint angle there. And with this, we can consider that this one is about a conical scanning tracking radar that will be useful for the tracking the missiles or tracking the uh, that any target. With this, we stop here. So thank you all.